Hello everyone and welcome back to the channel. This is Physics Junction with Mohammed Talha, and today we're going to be something that is of popular request, the most recent paper at the time of the making of this video, which is March 2025. And this is the paper. Again, it's going to give you a really good idea of what the examiner is basically feeling like before this exam session, what are the type of questions that could come in. So let's get started with this. Explain what is meant by the accuracy of a measured value. So we know that accuracy and precision are two common terms asked, or basically they are like really closely linked, whereas precision is basically how close the measured values are to each other. Accuracy is a measure of how close the measured value is to the actual value. So to the actual or the true value. Two solid cubes are measured to determine the density of their materials. 1.1 shows that the measurements for cube A are shown. So length of each side is given 1.53 plus minus 0.01. Mass is given as this. Show that the calculated density is given by is equal to this. So rho equals mass over volume. Because this is a cube, then I know that the volume would just be equal to L cube, the cube of the length. If this is asked in, so this is asked in kg per meter cube. So this is totally up to you. I personally prefer the final conversion for from grams per meter cube to kg per grams per cm cube to kg per meter cube. That's what I'm going to do. Just multiplication by 1000. Alternatively, what you could have done is you convert the mass to kg, which is into 10 to the negative 3, and when you do cm cube to meter cube, that would be 10 to the negative into 10 to the negative 6. So overall that becomes times 1000. So it's the same thing either way, and using this your answer should be correct to 2SF. It should be equal to this. Calculate the percentage uncertainty in the density of material of cube A. So I can see that density was calculated by mass over volume. So I can say that the percentage uncertainty in density is percentage uncertainty in M plus percentage uncertainty in volume. And because volume is calculated by length, I can say that's percentage uncertainty in M plus 3 times the percentage uncertainty in L. So M is 0.5 over 31.3 plus 3 times the percentage uncertainty in L, which is 0.01 over 1.53. Because there was a times 100 with both, so I can just factor that out as common. And then the percentage uncertainty using this, that turns out to be, that is 3.56. So you can say 3.6 or 4%, because percentage uncertainty are usually given to 1SF, but you can also write it to 3SF up to 3SF. So you can also write 3.56. That would also be correct. Density of the material of cube B is determined to be 9.2 into 10 to the 3 plus minus 6%. State and explain whether cube A and cube B could be made from the same material. So when we talk about material properties, the density should be approximately the same, but because we have ranges here, so maybe because of the experimental procedure, how the densities are determined, maybe they could be lying in each other's range. So let's check that out. So let's see if obviously 9.2 into 10 to the 3. Okay, so let's do this. So 8.7 into 10 to the 3, let's find this percentage of this, and because this is smaller than this, let's try to add this to this value. So adding 4% basically makes it 1.04. So 1.04 into 8.7 into 10 to the 3. So let's try to do that. So this turns out to be 9.048. So 9.0 into 10 to the 3 kg per meter cube. Let's now, because this is a smaller value than this, so let's see if the lower bound of this, the lower value, if it basically falls into this range, right? So this can go as high up to 9.0 into 10 to the 3, and let's see how low this value can be. So minus 6% would be 0.94 times 9.2 into 10 to the 3. Let's see what this turns out to be. So 0.94 into 9.2 into 10 to the 3. So this is 8648, so 8.6 into 10 to the 3 kg per meter cube. So yes, they could be made from the same material. Because ranges for both densities, scroll up, because ranges for both densities overlap. All right, so that's this one. Let's go on to question number 2. State the principle of moments, a very typical sort of question which is asked again and again. You must know how to ace this. So you say that for an object in equilibrium, sum of, or you can say total, clockwise moments about a point, and you need to say this, about a point, equals sum of anti-clockwise moments about the same point. All right, so you also need to say that for a body in equilibrium, for an object in equilibrium, and then you also need to specify that the clockwise and anti-clockwise moments have to be about that same point. Let's go on to the next one, part B. A solid plastic cylinder floats in water. It is used to support one end of a horizontal uniform beam AB. So if it's uniform, that means that if this has a length of 6 meters like this, which is also given here, and weight 1700 newtons, so its weight would be marked halfway along the center. So this length is then going to be 3 meters, and then this length is also going to be 3 meters. The cylinder is floating vertically in the water. Top of the cylinder is attached at its center to the beam at a horizontal distance of 5 meters from end A. The cylinder applies a vertical force of 1300 Newton to the beam. So this force is acting like this. This is 1300, this is 1700. And a person of weight 660 Newton stands on the beam at point P. Beam AB is in equilibrium. So we have those two conditions for equilibrium: total forces, so resultant force is 0, resultant moment is 0. And resultant moment is 0 is basically just saying that the principle of moments apply. By taking moments about A, determine the distance x from A to P. Alright. So moments about A, I know this is 1700 and the weight of the person is 660. So then, before using the principle of moments, I should see which one produces a clockwise moment, which one produces an anti-clockwise moment. This is clockwise, and this is anti-clockwise, right? So then I'd say that the moment because of this should equal the moment because of this plus the moment because of this. So then I'll write the expression. So that's going to be, so I'm doing anti-clockwise moments first. So I'll say 1300 times 5 equals, this is 1700 and this would be 3 as I just said, so equals 1700 times 3 plus 660 times its distance from A, which is x. So plus 660 x And from here, you just rearrange and find out what you need to. So 1300 times 5 minus 1700 times 3 divided by 660. So x turns out to be 2.12. So 2.1 or 2.12 both work. And that's your answer for this one. Let's go on to the next part. Bottom of the cylinder is submerged in the water to depth y as shown in 2.2. The beam is still attached to the cylinder but not shown. So by Newton's third law, you can see that the force which the cylinder applies on the beam applies an equal force on the cylinder downwards, which is 1300. This width is given. So the cylinder has mass 11 kg and diameter 0.78 meters. Beam exerts a vertical force of 1300 Newton. The cylinder is in equilibrium. Show that the upthrust acting on the cylinder is 1400 Newtons. So if this is in equilibrium, this is pretty straightforward, that the weight would just be equal to the upthrust, and there's also the 1300. So upthrust is upwards and then weight is downwards, and that force 1300 is also downwards. That's okay, I've written it the other way around. So U is W plus 1300. So W is 11 times 9.81 plus 1300, and that should be equal to this. The water has density 990. Calculate the depth y. So now that I know the upthrust, which is approximately 1400, I need to use the formula rho g delta v, where delta v shows the volume of the object which is actually beneath the water. So in this case, I think it was fully submerged, right? Okay, so it's not fully submerged. It's only submerged to this depth y, right? So only this part is what is actually under. So it's this depth and this is the diameter. So using that, I can find the area, and then I can multiply by this to get the volume, right? So this is 1400 equals 990 times 9.81. The length was y and the area is going to be pi d square over 4, pi into 0.78 squared over 4. And from this, you just try to make y the subject of the equation. So 990 times 9.81 times pi into 0.78 square over 4. This is 4640. 1400 divided by this, that turns out to be 0.3016, so 0.30 meters. The person can stand anywhere between A and B. On 2.3, sketch the variation of the depth of the bottom of the cylinder with the distance of the person from A for distances between 0 and 6 meters. Numerical values are not required. Okay. Now let's think about this one. So it's the depth of the bottom of the cylinder with the distance of the person from A. Okay, so the depth of the bottom of the cylinder is this, right, which was initially y. And this is to be plotted against the distance from A, which is x. So what I just saw was this, that basically, okay, so first of all, let's think about this. The depth of the bottom of the cylinder is basically what I just used for the upthrust calculation. So the depth, I can say that for the purpose of the graph, because u equals to rho gv, and we just use this as rho g y times its cross-sectional area. So this is basically linearly proportional to the depth, which is just called u. So I can imagine that this is the graph of upthrust, and the distance from A in meters. So the distance from A is this, which is x. Right now it turned out to be 2.1 when the upthrust was 1300, but we don't have to plot values. So we did have to plot from 0 to x. So I can say that this 1300 force, which was basically, if I look here, that's u minus w, right? So I can say that this is, let me write this here. So u minus w times 5 equals to 1700 times 3 Let's actually do this. So 1700 times 3 is 5100, and this is 660 x, and I actually also know w, right? So u minus w times 5, w was 11 times 9.81, 11 times 9.81 times 5. This is being subtracted here, so on the other side it would go and add up with the 5100 plus this. So u equals to, this is the equation that I get, so u equals to 660x plus 5639. Again, this is what you should do in order to know what to plot against what. This is really on my y-axis, and this is really what's on my x-axis. So this is the gradient, so it's positive. And most importantly, I can also see that this is a straight line, and this right here is the y-intercept. So y-intercept, gradient. So I know this is going to start from a non-zero value because there is a y-intercept. You could have also done it this way, that even if 660, and if I make x 0, even then I get some value of the depth, right? So I get some value of the depth even then. So what that means in this case is that even when x is 0, so even when this guy is standing right at the pivot, so his weight is not producing a moment, there is some force here, which is the weight, and there's this upward force, right? And this downward force is going to take the cylinder slightly below the surface of the water. So there's going to be some depth. So it's going to start from a non-zero value, and apart from that, it's going to be an upward sloping line. That also makes sense according to intuition, because the greater that this distance gets, so the clockwise moment increases, the anti-clockwise moment must also increase. So this force must increase. This force is basically coming from the upthrust, which is that upward force, and that increases with depth. So that's why it's supposed to increase as well. And it also makes sense that why it should be a straight line, because of everything being linearly related. So this graph is then supposed to be a line that goes like this. And this is what you plot. Let's start with question number 3 now. A truck R of mass 9400 kg moves with constant acceleration in a straight line down a slope as illustrated in 3.1. So we know the distance at point A, the speed of the truck is 13 meters per second. At point B, the speed of the truck is 22 meters per second. The distance between A and B is given, and you have to find the acceleration. I think this is pretty obvious that this is a question on equations of motion. The initial speed u is 13. The final speed v is 22. The distance is 180, and we are supposed to find the acceleration. So the equation of motion to be used is v square equals u square plus 2as. So a is v square minus u square over 2s, which is 22 square minus 13 squared divided by 2 into 180. So using this, you find out the acceleration, which turns out to be 0.88 meter per second square, correct to 2SF. Determine the gain in kinetic energy of the truck between A and B. So the gain in kinetic energy, I can use this formula for it, which is half m v square minus u square. Alright, so you have to keep in mind that it's not half m v minus u squared, it's half m v square minus u square. So you first square the speeds and then you subtract. So the mass was given as 9400. Final speed is 22, so 22 squared minus initial speed squared, which is this. And then you try to find out the, you plug all of this into your calculator, and this turns out to be 1.5 into 10 to the 6 joules. Let's go on. Part B. A short time after passing point B, truck R moves in a straight line on horizontal ground. The driver of the truck applies the brakes. 3.2 shows the variation with time of the momentum of the truck. So this is momentum in 10 to the 4 kg meters per second, and on the horizontal axis we have time in seconds. So this is the momentum time graph. Remember that for a momentum time graph, the gradient is the resultant force. And as you can see here, the momentum is decreasing. And if I also think about it, when I try to find the gradient at any point, because of how the shape of this particular graph is, the gradient at any point is negative, which means the force at any point is negative, and the force being negative just means that the force is acting opposite to how the object is moving. So this force is actually going to make this truck decelerate. Then it says in part 1, define force. So force is defined as the rate of change of momentum next part, show that the average resultant force between 0 and 15 is negative 1.2 into 10 to the 4. Alright, so again the idea is that because we need the average force and not the force at any instant, I can assume a linear change like this. So if it starts from here and it's going like this, I can assume that this is how things go here. So this initial value was, I think, let me scroll up. So this is going to be 22.5 in the middle here. So this is 20.5 and this is 21. And then this value is, so this is 2.5. So then this must be 2. Right? So if I find the gradient, so rise over run, right? So I can say that this coordinate is basically 0, 21. This coordinate is 15, 2. So you do change in y over change in x. So 21 minus 2 over 0 minus 15. So I'll write that gradient is a resultant force so that's 21 minus 2 over 0 minus 15, which turns out to be, and also there was a into 10 to the 4 with the y, there's also this here, into 10 to the 4. So this turns out to be approximately this much. Okay, so I'm actually getting 1.2 into 10 to the 4. Let's make sure that we haven't made a mistake here. So this is 5, right? Okay, this is 5. So 1, 2, 3, 4, 5. Okay, my bad. So this is not 2, then this is 2.5. So let's correct that. So we weren't reading it properly. So this is 2.5. And when you do this using 2.5, then your answer turns out to be 1.233. So then that becomes what you want. Which is this value right here. Right? Then your answer turns out to be this. Next part. An identical truck S has the same initial momentum as truck R. The truck S experiences a constant force equal to the force in B2. State and explain whether truck S will take more, less, or the same amount of time to come to rest as truck R. So first things first, if the truck is identical and it has the same initial momentum, so this means that according to our equation where we talk about change in momentum, which is PF minus PI, so initial momentum is the same, right? And both of these, we're talking about these coming to rest, so PF is also the same. So delta P is also the same for both of these. And we have to comment on the amount of time, so let's think about this in terms of this equation. Alright, okay. Now when we talk about this, let's look at this. If we wanted to talk about this truck, the original truck which was R coming to rest, then we would look at the entire gradient from here to here, right? Now this one you can see has an obviously lesser overall force, a lesser resultant force. But when we talk about this one, the new truck, we wanted to experience this force in green, right? Now because this gradient is steeper, that means that the force which is acting on S is more, right? So the average force on S is more, whereas the average force on R to come to rest is less. All right. So when I think about this equation, and right now I'm talking about S, so delta P is the same. For S, the force is more, so the time taken would be less. This is the entire reasoning for this part. So I'll say this, that change of momentum is same for both. A greater average force acts on S as compared to R, which we saw using the gradients. So it will take less time to come to rest. All right, and also if you don't like this reasoning of looking at the graph, then you can also say that all right, for this new one I know that the resultant force is this, right? So then you would talk about it like this, that all right, F equals to delta P over delta T. So we're talking about S right now. So for S, if we want to find the time, then this would be delta P, but this time it would not be minus 2.5, right? It would just be 21 into 10 to the 4 divided by the force, which was this 1.2 into 10 to the 4, and you would find this value to be less than the time taken for R to come to rest, because this value turns out to be 17.5. But if I look at the graph, R actually takes more time. So this is like what, maybe like 23, yeah, 23 seconds to come to rest. So this, okay, this is 23. So this is 23 seconds to come to rest. So this one actually takes less time. And again, it's the same reasoning, right? So if you want to refer to the equation, you can. If you want to give calculations, you can. I just found the graph reasoning to be a bit more straightforward. But again, I think that with this part, what made it more difficult was basically reading the or comprehending what the question actually had to say. So it's easy to misunderstand this. Let's go on to question number 4. A device containing a microwave emitter and receiver is placed in front of a large metal sheet in a vacuum as shown in 4.1. So we have a microwave emitter, we have this metal sheet. The line XY is perpendicular to the metal sheet. Device emits microwaves of frequency 6.3 gigahertz. When the device is at position P, a stationary wave is formed between the device and the sheet. Explain how the stationary wave, including the nodes and the antinodes, is formed. And this is a 4-mark question. So we are used to answering this question as to how the stationary wave is formed. But how do you answer this regarding where the nodes are, where the antinodes are, right? So this is what we need to comment on. So let's just first write what we know, which is that the microwave is incident on the screen, on the sheet, and gets reflected. The incident and reflected waves superpose, or you can say overlap, or you can say interfere, or all of these are acceptable. I like to say superpose. And then you have to talk about the nodes and the antinodes forming, right? So we don't know exactly what sort of a harmonic is forming here. So we need to talk about something very general. So what we'll end up saying is, again, we don't know which harmonic is going to form here, but what I do know is that there's going to be some wave which is emitted, and there's going to be some wave which is reflected. Now there's going to be this idea that when the waves are reflected, So let me make the reflected wave here. So the incident and the reflected waves superposed, we know that in terms of the time period of these waves, the stationary wave takes up different shapes, takes up different forms, depending on what the phase difference is between the incident and the reflected waves. I know when the incident and the reflected waves are going to be in phase, so when the phase difference is 0, then there's going to be an antinode forming where they are in phase, right? So where the resultant amplitude is a maximum, I know that's going to be that's going to be an antinode. And similarly, when they meet out of phase, so where the waves are 180 degrees out of phase, that's where we'll be having nodes, right? So this is just what was required in this part. So I'll say that when the incident and reflected waves meet in phase, antinodes are formed, and then similarly, when the incident and reflected waves are okay. So I know that basically antinodes can so nodes are always going to be there, right? It's always going to be at the same position, whereas antinodes could either be up or down. So I can say that antinodes are so the nodes are formed where the waves are always out of phase. So when the incident and reflected waves are always in antiphase, so exactly out of phase, or you can also use angles here, nodes are formed. All right. Calculate the wavelength of the microwave. So I have the frequency here, 6.3 gigahertz. So I need to find the wavelength, which is not very difficult. So V equals to F lambda. Because this is a part of the EM spec, I know its speed is going to be the speed of light. And the frequency is 6.3 giga, which is 10 to the 9. So lambda turns out to be 0.048 meters. Next, at point P, the receiver detects a max amplitude of the stationary wave. Device is moved slowly from P along the line XY, and the receiver detects a series of min and max amplitudes. The first time a minimum amplitude is detected by the receiver is when the device is at point Q. So it detects a max at P and then a min at Q. Let's just go back to the diagram for this. So max at P, so this is an antinode, and a min at Q, this is an antinode. So I know node or antinode distance is half the wavelength, and this is going to be even half of that, so this is lambda by 4. Right, so I already have lambda, so the distance between P and Q is going to be a quarter of that, so 0.048 divided by 4, which is 0.012 meters. Intensity of the microwaves is emitted by the device is increased. So whenever you see the word intensity, the other term that should pop up in your head is amplitude. So intensity being increased means that amplitude is also increasing. Frequency of the microwaves is unchanged. The device is moved slowly along the line XY from point Q until the next max amplitude is detected at point R. State and explain whether the distance QR is greater than, less than, or the same as PQ. All right. So when we talk about the distance which is formed, so that's basically because of the wavelength, right? And the wavelength is then linked to the frequency by this equation. So there's nothing related to the amplitude in this, right? So the frequency, or you can say that since the wavelength is unchanged, so the distance is the same, it does not depend on amplitude. So I'm going to say that since the frequency of the wave is unchanged, the distance QR, right? So Q was our minimum, R is our maximum again, and previously P was our maximum. So the distance between the max and the min, the distance QR is the same as PQ. Let's go on. Question number 5 now. A stationary loudspeaker emits sound of constant frequency. A microphone is placed near to the loudspeaker and connected to a CRO. Trace on the screen of the CRO is shown in 5.1, and you also have the scale shown here. Time base is given, speed of sound is given, and we need to find the wavelength. So first we need to find the time period using what we see in the graph, right? Now this grid is a little bit messed up, but what we can see, let's look at that. So 1 cm is basically 1, 2, 3, 4, 5 boxes, right? So let's see. So this is like 1, 2, 3, 4, 5. That's 1 centimeters. 1, 2, 3, 4, 5. That's 2. 1, 2, 3, 4, 5. That's 3. So it's 3 for half a wave. So I know that for what do you call it? So it must be double of that, but actually I was just looking at this, and what I saw is that this distance, if you count this is like 29 small boxes. And again, this is because the grid looks a little bit messed up. Can't help that. So this is not actually, by the way, how this is in Cambridge. This is just how I got it. So 29 divided by 5 gives me the number of centimeters. So that is actually, if I use the time period formula, so that's going to be the number of horizontal divisions, which is 29 over 5, which is I think 5.8, and this is the time base, so 5.0 into 10 to the negative 4. So from this the time period turns out to be 2.9 into 10 to the negative 3 seconds. And now I need the wavelength, so V equals to lambda over T. So lambda equals Vt. So I just multiply this and this value, and the answer I get is 0.96 meters. Next, the loudspeaker now moves in a straight line while emitting the same sound of constant frequency. So now the source has started to move. The concept at hand that you must then apply is the Doppler effect. So you say that this loudspeaker now moves while emitting the same sound of constant frequency, and the period of the trace increases continuously. Alright, so if period is increasing, that means the frequency is decreasing, right? So the frequency is decreasing. So also the frequency is not just less, it's also decreasing, right? So if the frequency was just less, I would say that alright, it's just moving away at constant speed. But because the frequency is continuously decreasing, that means it's speeding away from the microphone. Alright, there are two things to keep in mind here. When we talk about the Doppler's effect formula, we say that alright, if the observed frequency is FSV over V plus minus Vs. Because here the observed frequency is less, I end up concluding that we are moving, away from the source, right? So it must be plus Vs, so it must be moving away, right? But because this is continuously decreasing, this means that the speed of the source must be continuously increasing, right? So it's increasing speed, but it's moving away from the observer, which is in this case the microphone. So you'll say that the loudspeaker accelerates away from the microphone. So probably this is what the mark scheme says for this, is that one mark for saying that it's moving away, and the other mark is for saying that it accelerates, which makes up this total of 2. Let's have a look at question number 6. A cylindrical copper wire P of length 0.24 meter is shown. Current in the wire is 0.85 amperes. Resistance of the wire is 3.3 milliohms. Total number of charge carriers is this much. Now again, if you've done a lot of practice, you know that you need to be aware of this, because when we use this equation, and I know it must be used in some part because the examiner has given us this. So in this equation, small n is basically the number density, which is the number of charge carriers per unit volume. So I need to divide it by the volume if such a question is going to be asked, and it will be asked. Part A says calculate the potential difference between the two ends of wire. So I know the current, I know the resistance, so I just need to use this formula. 0.85 times 3.3 into 10 to the negative 3, and this turns out to be 2.8 into 10 to the negative 3 volts. Show that the cross-sectional area is this much. So for the cross-sectional area, this is worth 2 marks, alright? So what do I know? For the cross-sectional area, I know the resistivity as well. Yeah, I totally forgot about that. We know the resistivity, we know the resistance, we know the length. So finding the area is not very difficult, right? So we use this formula that R equals rho L over A. So A is rho L over R. Rho is 1.8 into 10 to the negative 8. L is 0.24 and R is 3.3 milli. And from this, I'll just find out what A is. So this turns out to be this corrected to SF. Now this one, show that the number density of charge carrier. So this is good because the examiner has actually given this hint to you, and this is a show part. So you automatically realize that, all right, I did need to divide by the volume. So small n is the total number of charge carriers divided by volume. The volume would be the cross-sectional area, what you just found out. Preferable to use the calculator value times the length, which was 0.24. And the total number of charge carriers is 2.6 into 10 to the 22. 2.6 into 10 to the 22, and that must be equal to this value right here. Next it says calculate the average drift speed. So average drift speed, I equals A N V Q. So V equals I over A N Q. Current was given above, which is 0.85. Our area was this, 1.3 into 10 to the negative 6. N is 8.3 into 10 to the 28. We're talking about electrons. So for electrons, the charge on one of these is given in your data sheet, 1.60 into 10 to the negative 19. And then you plug all of this into your equation, and the value that you get is 4.9 into 10 to the negative 5, which does make sense if you think about the typical values for the average drift speed. So that is usually in 10 to the negative 4 or 10 to the negative 5. A different copper wire Q has the same volume as P but non-uniform radius as shown in 6.2. Radius R1 at end X of the wire is the same as the radius of wire P, and then it basically starts to narrow down, and the radius R2 is less than R. So for P was actually a uniform wire, right? So it has a uniform radius, and it says that R1 is basically the radius of P. So when I talk about P, that means that P is basically a shape like this, right? So this is P. This is what P is supposed to look like. And then R2 is less than R1. State and explain how the resistance of Q compares with the resistance of P. Now obviously I must use this idea that alright, I can't just look at the radius for this. For Q, I must talk about the average radius, right? So I'll say that the average radius is less for Q as compared to P. So average radius of Q is less then average, then the radius of P. I don't need to use the term average here because that was constant. Now I need to explain how the resistance compares, right? So resistance is rho L over A. So I can say that because its radius is less, its cross-sectional area, the average cross-sectional area is also going to be less, right? But it says that it has the same volume, right? So this is also an important thing. So area being less means that the length must go up because of this, right? This is not a exact two-scale diagram. This is not two-scale. It's just showing you the shape of the cross section. So if the area of Q is less because of the radius being less, then its length must be more. So length is more, area is less. All of this causes the resistance to be more, right? So this is what I need to explain now. So I'll say that average radius of Q is less than the radius of P. So the cross-sectional area of Q is less than the cross-sectional area of P. And then I must say that since volume is constant, Q must have a greater length. And then I'll refer to the equation that I used above, that since R is proportional to L over A, the resistance of Q is more than the resistance for P. Okay, next. On 6.3, sketch a graph of the variation of the average drift speed of the charge carriers with distance from end X of wire Q. So we now have to sketch the average drift velocity for wire Q, which has a non-uniform cross-sectional area, right? So I think about this equation, I equals to A N V Q, and I need to plot V, so let's make that the subject of the equation. So that's I over A N Q, right? And now I need to plot this. So first of all, I know that in this case it must not start from 0, right? Even as it enters the conductor, it would have some average drift speed. Now it could be here, it could be here, I don't know, but it's going to be non-zero, right? And now I need to think about what's going to happen to the average drift speed. So I can see here that the cross-sectional area decreases, so I'd expect V to increase. But if I think about area, does it linearly decrease? And the answer is no. That's because there is this thing that area is equal to pi r square, right? So because the radius is decreasing, yeah, so the radius can decrease linearly, as was also the case because it was uniformly narrowing out like this. But the area is decreasing by a square proportion, so that means the area is going to decrease really fast. So the speed is also going to increase really fast. So it's going to be an upward sloping curve that looks like this. So this was also a question that required a bit more of thought. Let's look at the last question, question number 7. An isolated stationary nucleus Q decays into nucleus R and an alpha particle has the speed. Complete the equation for this decay. So alpha decay, I need to complete the equation. So I know this must be 86 here. So that 86 plus 2 becomes 88 and 222 plus 4 makes it 226. By considering momentum, calculate the speed of nucleus R after the decay. So initially your nucleus Q was stationary. So that means R and alpha must have equal momentum in opposite directions by the conservation of momentum, right? So this is what I needed to realize for this one. So I'll say that momentum of R equals momentum of alpha, right? So for R, it has a mass of 222, so 222 u multiplied by its speed, and this is what we need to find, equals to the momentum of alpha. So the mass of alpha is 4u and its speed is 1.5 into 10 to the 7, right? So u's cancel and I need to find v, so that would be 4 divided by 222. So let's do this together. Into 1.5 into 10 to the 7, which turns out to be 2.7 into 10 to the 5 meters per second. State 3 quantities that are conserved during this decay. So there is a lot that you can say. You can say that momentum is conserved, you can say proton number is conserved, and you say nucleon number is conserved. Right? This is the more obvious choice in this case. You could have also said something like this, that charge is conserved, and you can also say this, that mass energy is conserved, but make sure that you don't just write energy or mass, you say mass energy is conserved, right? E equals to mc square, so you can also say that. So that was this entire paper, and I hope that this helps you a lot while setting for your May-June exams. Best of luck for that, and I'll see you in the next one.